Alright, for today, we're going to discuss theorem 513, 514, and 515. Ha! Alright, here we go.
Question: is this the last chapter we learned, like the last, like?
No, we learned pieces of chapter 6 as well.
Dang it.
Pieces. Yes, we don't go through the entire chapter 6. Okay. Applications of integration. Actually, it's pretty fun. I like it. Okay. Theorem 513. So, as we talked about on Friday, this section deals specifically with non-base E problems. Ladies. So, for these kinds of problems, these are going to be some derivative formulas that work very well with bases that are non-E. So these will be base formulas for your standard exponential, so a to the x power, as well as bases for logs of different bases. So each one of these you'll notice is very similar to one that already exists, because again, different bases that are similar to E will have similar properties just with small modifications. Let's take a look at theorem 513. Theorem 513 has 4 parts to it, 2 parts for the exponential, 2 parts for the logarithmic. So part 1, the derivative with respect to x of the function a to the x power is equal to natural log of a times a to the x power. Part 2, if, on the other hand, instead of being a to the x, it's a to some function, then the derivative would be the natural log of a times a to the u, and then chain rule would imply that the derivative of u goes to the end. So du dx or u prime. So we have any base that is not e. So base of 2, base of 3, base of 5, base of 7, base of some round decimal. So you take the derivative. The logs, very similar. So derivative with respect to x of log base a of x is equal to 1 over ln of a times x. Part 4, if the inside is a function, so log base a of u, this is of course 1 over ln of a times u times du dx. You could also move the du dx on top, which is the common thing that I do to make this a little simpler. It depends on how nasty u is, whether you want to do that now or later. So, these are derivatives for logs and exponentials of not base e.
Attention, Coach Kane's health class is in the track. Coach Kane's health class is at the track.
So, pretty straightforward. Let's look at some derivatives. So, let's start easy. If I have the function f of x is equal to 3 to the x power, if I have the function f of x is equal to 7 times 2 to the x squared minus 2x, top one's easy, second one not. So, I have to do 2 logs as well. Function f of x is equal to log base 4 of x, and then a more complicated one, log base 3 of x times x plus 1. Alright, ready? So you can derive each one using our rules. So, again, the properties of these are pretty straightforward. There's just a natural log in there. You'll notice that it's very similar to the change of base formula. And in fact, it is one of the tricks you can use to simplify this. If you were to rewrite each of these problems as a change of base problem, you would eventually end up with the same derivative when you took the derivative. So remember your change of base formula from algebra 2. If you did that for each of these problems, it would still be. So you have to make sure to change the base to e instead, and you get the following results. So the first example, f of x equal to f, or 3 to the x power. The derivative of that function, so f prime, would be equal to. So since this is a base that is not e, it's 3, I use that first version of the formula. If the function is a to the x power, then the derivative of that function, f prime, would be equal to ln of 3 times 3 to the x. Note, if you assume if you assume your a value in this function is e, then it actually gets back to the original derivative we talked about. Because if you assume a is e, then when you plug it in, ln of e is what comes out in front, ln of e is 1, and then you have e to the x, so you end up with the derivative of e to the x is still e to the x.
So the way you write it there, is it just ln of a times a of x? Or
Yes.
ln of the whole thing?
Ln of a is its own thing, separate.
Ln of 3 there is its own thing.
Yep. Let's think of it like a constant. Because remember, ln of 3 is a number. So it's a number times 3 to the x power. My second one. So remember, constants can be pulled out. So f prime in this case would be 7 times. Now, what goes in first is the natural log of the base. So this would be ln of 2. So that's also a constant. So I have a constant times a constant. I can leave those there. And then I use my actual function, 2 to the x squared minus 2x. But I must make sure, since this has a function at the top, to multiply it by the derivative of that function, chain rule. Take the derivative of x squared minus 2x, 2x minus 2. So all 4 of these pieces end up being multiplied together. The 7, the ln of 2, the 2 to the x squared minus 2x, and the 2x minus 2, all as one big problem.
So if you were to take a second derivative,
I'd have to do a product rule if I was taking a second derivative.
but could we pull out 7 and ln?
Yes, and 2.
2.
Yep.
And 2.
So another way to write this function, I pull the 2 out, I pull the 7 out, and the ln of 2 out. This would be 14 ln of 2 as one big constant times 2 to the x squared minus 2x times x minus 1. So this 14 ln of 2 would be one big constant, and you have a function and another function. The third one, log base 4 of x. So again, I get my logarithmic formula. It says if I'm taking the log base a of a function x, it is equal to 1 over ln of a times x. So this would become f prime would be 1 over ln of 4. Again, ln of 4 is a constant, separate from everything else, times x. And there's my derivative. Relatively straightforward. You always want to check to see if it simplifies. Usually it won't, because if you're using this technique, it's because the number isn't e. So when you take the ln of 4 is going to be a decimal subtract. Always, always. My second one. Now, with these logarithmic ones, it is important to note that you can, and often should, simplify algebraically first. Rewrite this function before you bother trying to apply any rules. Otherwise, your u prime can be very nasty if you're not careful. Like this example. There are 2 ways I could simplify this algebraically to make this much nicer and cleaner. I'm going to ask now for suggestions. What's one way I can simplify this? I can distribute. I can hit the x times both terms, right? That would change this from log base 3 of x times x plus 1 to log base 3 of x squared plus x. This is much easier to do. Because when I try to do u prime later, du dx, it is a much easier u prime to do, because it's just a number minus another number, which has a very simple derivative compared to a product rule, which is what I have to do otherwise. There is a secondary option. This is option, let's call it A. And we will take this derivative here in a second. But there is an option B, which I'll show here in a moment. So, with this first one, if I didn't see that there was a trick to it, allow me to show you what this looks like. F prime is equal to 1 over ln of 3 times x plus 1 times the derivative of x times x plus 1. So I have to do the product rule. Left d right, plus right d left. And I end up having to simplify a bunch of stuff. And if I drop parentheses in the wrong spot, I might make some mistakes. It gets nasty real quick. If instead I do what Ricky suggests and distribute this thing through, it's much easier to do. So f prime becomes instead 1 over ln of 3 times x squared plus x times the derivative of x squared plus x, which is 2x plus 1. Now, I don't like this version. You'll see that I rarely use this version of that fourth formula. Instead, I would move it to the top. 2x plus 1 over ln of 3 x squared plus x. I prefer that version. That is because that's what I was trained to do. I do not say it's better. It's how I prefer it. When I grade either way. It doesn't matter to me. It's all the same. Now, this is both grade answers, both using option A as our way of simplifying. That was not the only way to simplify this function. So Ricky, you gave what I would consider to be the algebra 1 way to simplify this. Okay, he distributed. That's algebra 1 technique. Works great. Let's look for something a little more advanced. How else could I simplify this function, the original function? Log base 3 of x times x plus 1. Split it into two logs. This will become log base 3 of x plus log base 3 of x plus 1. Remember, multiplication becomes addition. Now, each of these is much simpler to do. This first one would become 1 over ln of 3 times x, because that one is just your basic rule 3. The second one, plus 1 over ln of 3 times x plus 1. The derivative of x plus 1 is also 1, so that's actually fine. This is the other correct solution. I like this version better because there's fewer chances to mess up the chain rule. And the chain rule is easier to do. So, like I said, you can choose to simplify or not simplify. The book strongly recommends simplifying somewhere. Which method doesn't specify, it just recommends doing one of them. Questions?
If you were to simplify that, would you have to multiply the left side by x plus 1 and the right side by x?
Yes, on top and bottom. They would eventually become the same thing through some creative math. But yes, that's exactly what you have to do. Other questions about Theorem 513? Okay. Now let's look at the second part of 513, which is the only part that this talks about it, which I find very strange. Because if you notice, a lot of these look very similar to problems we've already done. Which means that if I was to undo this using the second fundamental theorem of calculus, meaning I was to undo these derivatives, a lot of these would probably not end up back here. Example, this third one. If I was to undo this rule, 1 over ln of a is a constant, we could pull it out and then end up with a natural log function very nicely from section 1 of this chapter. Much easier to do. That's not what we started with. Again, it's a change of base to get back to it. But that means that for a lot of these, there's no great integration rules to match with them, except one. This one. This one has a very nice integration rule that goes along with it. Now, we talked about, back in chapter 4, that there was a simple integration rule that applied to power functions. This also applies here. So, the only integration technique we're going to talk about in this section that is new, so again, all the old integration techniques still work, is the integral of a to the x power dx. Now, obviously, there's still u substitutions that can work with this. There's still a lot of other alternatives we can try. But if you ever have a function a to the x dx, the integration of that function is 1 over the natural log of a times a to the x plus c. If you were to plug the right-hand side back into the derivative formula, you would get right back here, which is very nice, because that's what you're supposed to do. This is the only new integration rule. And it's not even a theorem, it's just a natural consequence because of the fundamental theorem of calculus. So this section has a lot of problems that do deal with integration. In those problems, most of them will involve this basic integral or involve some u substitution to get back to it. All right. Theorem 513 is done. Theorem 514. My plan is to finish all of the notes for this week today and spend the rest of the time working through homework problems throughout class. We're recommended pretty strongly this week to not assign new homework. I can't avoid it for this section because I forgot to assign it last week. Sorry. So, we started last week, still has.
Why are you recommending not to?
It's the last short week of the year. The principal suggested that we use this time that we have to allow students who are behind to make up work, which is what I hope you guys use the time for, since we're going to be doing most of the homework in class. I really strongly hope that some of you guys that are behind in homework get some stuff done and encourage me to grade it. All right, theorem 514. Yeah. Theorem 514. I knew there's a reason I was thinking of the power rule. This is alternatives to the power rule. Okay. Two parts again. First part, if I take derivative with respect to x of the function, x to the n power. So this is from way back in chapter 2. The derivative of x to some power. There's a general rule for this, which states that the derivative would be n times x to the n minus 1. Again, that's way back in chapter 2. Part 2 is the alternate form. So we've talked about u substitution a lot. This is one that we haven't talked about. The derivative with respect to x. If this bottom thing is a u. So a combination of the chain rule and the power rule together. N times u to the n minus 1 times du dx. Basic application of chain rule. I don't know why they're doing that here and not in chapter 4. But they do. Personally, I feel like it's kind of an unnecessary theorem. It's kind of obvious once you learn about the chain rule that this should be the case. So this is just the power rule combined with u substitution. So let's talk instead about theorem 550. Okay. Theorem 515 is the actual definition of E. So some of you guys might have been wondering how Euler came up with this number, how he got 2.717 as E and how he knew it worked. Well, he created a theorem that proved where E came from, and based on that theorem, used it to compute the natural logarithmic function and the exponential function. There are two versions of this theorem, one written in a very specific way, one written in a less specific way. If you look at them closely and apply algebra, you'd realize they are both the same thing, because they have to be. They both create E. So both of these are limits. So the limit as x approaches infinity but of the very unique function. So the first version of this states 1 plus 1 over x to the x power. Now, what we discovered was that if you apply this limit all the way out to infinity, you create e. For a long time, this is called Euler's theorem. Now it's just theorem 515. Kind of neat. The second version of this, again, if you look real close, you'll see that they're the exact same thing, just different versions, is x plus 1 over x to the x power equals e. Again, if you were to combine those two numbers into one fraction, you see that they're both the same. This is how e was first found. They applied a limit process and then used that limit process to find a solution and discovered that e was naturally created because of it. They knew it had to work because you take the root of this function, you end up with a natural log, a function that didn't theoretically exist yet. They were trying to prove it existed. And so they knew e was in here somewhere. And eventually they found it, which is pretty cool. There are some unique proofs online if you were to look it up, Euler's theorem. Euler had a bunch of theorems, so good luck trying to find this particular one, but kind of neat. If you look close, this is actually something you may have seen in another class. Accounting, maybe? This particular limit? Not the limit version of it, but something close to it. Perhaps with a different letter. Which is why this section has one last piece to it about compounding interest. Yep. So the compound interest formula is 1 plus r over n to the nt. It's a common compound interest formula. In fact, that's one of the formulas I have for you guys, which may be useful for this. Your interest, I always find it interesting that they called it A is equal to P times 1 plus r over n to the nt power. This formula is designed to calculate interest assuming that r is the rate, n is the number of times per year, and t is the number of years. So the rate has to be a decimal rate, not a percentage rate. I'll put that up there too. Rate as a decimal. Now, P is your initial investment, your principal. I think it's LE. Initial. There is an alternate version of this if you compound with both continuously.
What's n?
N, the number of times per year that you're compounding. If you're compounding monthly, you do it n as 12, because it's 12 months in a year, so 12 times. Do it daily, you'd have n be 365. Weekly, 52. Annually would be 1. Semi-annually, so semi-annually means every other year, so it'd be 0.5. Versus biannually, which means every half year. It's one of those two. I always mix them up. Bi is twice a year. Or
Fourth of the year. I had college algebra.
both. That is not. What? Semi cannot be 4. Because a semicircle is half a circle.
No.
Shenanigans are called. You're thinking quarterly. Okay, so fun English facts. Ready? Bi-weekly has two definitions that are opposites. Bi-weekly can mean twice a week or every 2 weeks. And there's no way to tell which one without context. Fun fact. Dictionaries are really helpful there. It literally says it works for both.
So I could say I go to the therapist bi-weekly, but you wouldn't know if it's 2 times a week or every other.
Yep. Which is why if you do technical writing for like an insurance company, or if you do it for like a claims company, you'll learn the phrase fortnightly, which means every 2 weeks, as opposed to bi-weekly, which could mean either one. Okay, back to our formula. There's one last formula up here. If it is compounded continuously, because of the previous theorem, this piece on the inside actually simplifies very nicely. It's called PERT. This is if you're compounding continuously. If you were to simplify this version of the equation, assuming the limit goes to infinity, therefore compounding continuously, then E does eventually appear.
Is the RT just part of the E or is it
Just E, just E. So this would be principal times E to the RT. So I guess like that. But nobody likes to write that. The E, RT is applied to just E. Mathematically speaking, for future reference, you see a formula in a book somewhere. Unless there's a parentheses, you assume it's applied only to the term itself. So unless it specifically wrote this, you assume it's for the E only. For future reference. I asked that same question in school. Okay, that is all the formulas and theorems for the entire week. Okay.
Is the homework for this section the one that you sent Friday?
Last time we read?
You said something in the school on Wednesday.
He said he was going to sign it right, so.
Oh.
So, once again.
What can I say? Okay. I'll be honest, I get distracted during engineering classes, and I'm like, oh my god, I get this done right now! And then I get thrown down, like, I'm gonna relax for a minute. And then I forget what else I have before that. Okay, your homework, which I will be posting here in a moment, rather than before you guys leave or before the end of the day, I'm gonna post it right now. Your homework will be out of the textbook, page 368. It'll be in 2 parts, 25 to 85. Odds?
We should make it shorter. Oh, that is pretty short. We should just leave it at that.
97 to 105 odds.
Oh, that's not bad.
What? It's like whole 5 extra problems.
There's some compounding interest ones in there.
I'm assuming there were problems.
Yeah, they're compound interest problems.
Why would you do that to us?
Because my hate flows strong. How else would I display my hate for the world? Then more math. Okay, let me post that on Google Classroom.